Hello, everyone. I hope you had a great day at DBTest, and I'm very sorry that I could not join you in person. Nevertheless, I'm happy to present our work on the analysis of geospatial data loading through this video recording. I am Eleni Dzirita Zaharatu, an assistant professor at the IT University of Copenhagen, Denmark. This is joint work with my master's student, Aske Vax. Applications in both science and industry accumulate large amounts of spatial data from a variety of sources. This includes scientific data, infrastructure and urban planning data, satellite images, social media data, data collected from smartphones and other GPS-enabled devices, and traffic data, just to name a few examples here. Efficiently managing and understanding this wealth of information is crucial for advancing research and improving practical applications across multiple fields. Spatial data comes in various file formats, such as plain CSV files, shape files, GeoJSON, GeoParquet, flat GeoBuff, and GeoPackage. At the same time, the landscape of spatial libraries and systems is also very diverse, with each system typically supporting only a subset of the existing file formats. Some example systems and libraries include the GDAL-OGR library, DACDB, GeoPandas, GIS software like ArcGIS, and databases with spatial support, such as PostGIS, Oracle Spatial, and SQL Server. With so many options, how do you choose the best system for a specific file format or the best file format for a given system? This is the question we explore in this paper. More specifically, we study the impact of system and file format on loading performance. As I mentioned earlier, efficiently analyzing spatial data is critical for many applications. The first step in any analysis pipeline is loading the data into the system that will be used for the analysis. Efficient data loading is crucial because it can become a bottleneck when dealing with large datasets. To quantify and compare the efficiency of different geometries, of different technologies, we need to establish benchmarks. While there are several benchmarks for spatial data in the literature, they focus on specific operations like spatial joins and topological relations. There are also studies on the performance of exploratory analytics workloads and a recent blog post examining the performance of writing spatial data using different file formats and libraries. However, no benchmarks specifically focus on data loading performance and the impact of file format. Additionally, existing studies do not examine what happens inside a processor core nor provide lower-level metrics. Our work addresses this gap by analyzing spatial data loading and the stress it imposes on a processor core. Here is the outline for the rest of the talk. After this introduction, I will present some background on the microarchitecture of an out-of-order processor core. Next, I will introduce the setup and methodology for our experimental study. Following that, I will show you the actual results, and finally, I will conclude the talk. Let me give you some background on out-of-order processors to help you put the results that I will show you later into some context. Out-of-order processors have two main building blocks, the front end and the back end. The front end prepares instructions for execution by fetching, decoding, and issuing instructions. Then the back end handles the actual execution and completion of instructions. The scheduler in the back end dispatches instructions to various execution units, and these execution units perform operations like arithmetic, logic, and floating point calculations in parallel. That's where out-of-order execution actually comes into play, meaning that instructions are executed as soon as their operands are available, rather than strictly following the program order. The backend also buffers outstanding data load and store requests to minimize stall time caused by memory misses. Finally, the backend ensures that instructions are committed in the correct order to ensure program correctness. Looking at the memory hierarchy, the first level of cache, L1, is split into instruction and data cache and is very small but extremely fast. Moving down, caches become larger and slower until we reach the main memory. Any delays related to preparing instructions like fetching and decoding result in front-end stalls. All other types of delay cause backend stalls. Moving on now to our experimental study, we used 3 different systems, DuckDB, GDAL OGR, and GeoPandas, to load 4 different file formats: shapefile, CSV, GeoJSON, and GeoParquet. On the hardware side, we use an AMD Ryzen 5000 series CPU with 6 cores and 2 threads per core. So since DuckDB supports parallel loading, we evaluated 2 versions of it, a single-threaded version and a multi-threaded version that uses all 12 hardware threads available. The other systems generally do not support parallel loading, except when loading GeoParquet files. So for GeoParquet, OGR uses a default of 4 threads and GeoPandas uses 6 threads. And otherwise, all other file formats are loaded single-threaded in these 2 libraries here, OGR and GeoPandas. Now, to test the loading performance, we generated synthetic spatial dataset using a tool called SpiderWeb. This is a tool freely available on the web, and it is developed by UC Riverside. You can see the web interface and the reference here on the slide. So using SpiderWeb, we created 4 polygonal datasets of increasing size with 1, 2, 4, and 8 million polygons. Each polygon has a maximum of 10 line segments, and the data distribution is Gaussian. So we exported the data from SpiderWeb in GeoJSON format, and then converted these GeoJSON files into the other file formats that we analyzed, that is CSV, shapefile, and GeoParquet. So in this table here, you can see the file sizes for the different dataset sizes and file formats. So moving from left to right, the file size increases, with GeoParquet being the most compact file format and GeoJSON the most verbose one. So looking, for example, here in the last row at the 8 million polygons, GeoParquet requires less than 1 gigabyte to store these 8 million polygons, while GeoJSON requires over 3 gigabytes to store the same amount of data. The main reason for that is that GeoParquet uses compression, and that's not the case for the other file formats. Additionally, we used a real dataset from OpenStreetMap, OSM, specifically the map of Denmark, which contains nearly 6.8 million features of various geometries. So here, the dataset, in addition to polygons, it includes other geometries like lines and points. So, as I mentioned in our analysis, we also examined lower-level metrics to understand what happens inside the processor. So we used the perf.stat tool to collect hardware counters. Implementation-wise, we wrote a Python script for each library that takes a file path as an argument and loads the corresponding file using that library. To ensure that disk I/O bottlenecks do not affect our results and our measurements, we first copy the file into main memory before loading it. We ran each experiment 10 times and report the average numbers. Next, I will present you the results of our experimental analysis. So in the first experiment, we measure the loading throughput of different libraries. The left graph here shows the throughput for our largest synthetic data that has 8 million polygons, while the right graph here shows the throughput for our real data set that has roughly 6.8 million geometries. Starting with the left graph first, the x-axis represents the different file formats. So we have CSV, GeoJSON, GeoParquet, and shapefile. The y-axis measures throughput in features loaded per millisecond. For each file format, there are 4 bars corresponding to different systems. So we have DuckDB, multi-threaded, and single-threaded. Then we have OGR and GeoPandas. Now, the key takeaway from the left graph is that GeoParquet provides the highest throughput across all libraries. Particularly DuckDB excels when loading GeoParquet files, outperforming other libraries by over 9 times in the multi-threaded setup and over 5 times in the single-threaded setup. This high performance is expected since GeoParquet is a compact and compressed file format, and all systems support some level of parallelism when loading GeoParquet files. But we can see that even without parallelism, DuckDB single-threaded achieves a high throughput for GeoParquet. On the other hand, GeoJSON shows the lowest throughput across all libraries, which again isn't so surprising given it is the largest. It has the largest size. It's more verbose in nature and requires string parsing during loading. Another interesting observation is that DuckDB is significantly faster when loading CSV files in the multi-threaded setup compared to the other libraries. Now, looking at the results for the real data set in the right graph, we observe overall similar trends. And again, here, GeoParquet achieves the best overall performance. So there is just a small deviation in the case of shapefile, where here we can see that OGR and GeoPandas exhibit better throughput compared to when loading GeoParquet, which wasn't the case before with the synthetic polygon data. Next, let's go deeper into DuckDB and examine some lower level metrics. For this analysis now, we focus on the single-threaded version of DuckDB, so DuckDB-ST, to avoid any thread interference. On the x-axis, we have different file formats, and then for each format, there are 4 bars representing the 4 different data sizes from 1 to 8 million polygons. The y-axis measures IPC, which stands for instructions per cycle, and this metric indicates the average number of instructions our processor executes per clock cycle. So a higher IPC means better performance, as it shows the processor can execute more instructions in a given period. Our AMD Ryzen processor can execute a maximum of 4 instructions per cycle, so that's the best we can achieve. And now looking at the results, we see that CSV and GeoJSON have high IPC values above 3. GeoParquet is lower, between 2.2 and 2.4. And finally, loading shapefiles has the lowest IPC. This suggests that shapefiles have more dependencies between instructions, which makes it harder for the out-of-order processor to resolve those dependencies efficiently. Another observation we can make here is that the data size doesn't significantly impact the IPC, except for GeoParquet, where we see the IPC slightly increasing with increasing data size. Our next experiment with single-threaded loading in DuckDB focuses on the L1 caches misses per 1,000 instructions, or MPKI for short. So we break these misses down into instruction and data misses. The x-axis shows the different file formats and data sizes, just like in the previous graph. And we measure the misses per 1,000 of instructions in the y-axis. What we see here is that L1 instruction cache misses dominate the total number of misses across all data sizes and file formats, except for GeoParquet here. Now, in general, we do expect to see a small number of data misses because we just load the entire file from start to end. That means that we access all parts of the cache lines brought in from a file page, and that leads to lower data misses per 1,000 instructions. Now, for GeoParquet, the reduced number of instruction misses likely comes from DuckDB's use of vectorized execution, which increases the instruction level parallelism. This is also consistent with the fact that we observe that the instruction misses for GeoParquet decrease as the file size increases, and it shows that as the data loading instructions are executed iteratively over more data, the overhead of other instructions that are outside the loading function, so other like startup and shutdown instructions, the overhead is amortized. Next, we expand our microarchitectural analysis to the other systems. The slide here compares the instructions per cycle, or IPC in short, when loading CSV and GeoParquet files using different systems. In the left graph, we focus on CSV loading, and the x-axis shows the different systems, and each system has 4 bars representing the different data sizes. And the y-axis measures the IPC. Here, we observe that single-threaded DuckDB achieves the highest IPC. However, the IPC drops for DuckDB in the multi-threaded setup, which indicates that there is some resource contention. The right graph shows the IPC for GeoParquet loading, and across the board here, the IPC is lower for all systems compared to when loading CSV files. Again, DuckDB single-threaded is the winner, and again, the IPC for DuckDB drops in the multi-threaded setup. Finally, we see a trend of increasing IPC with larger file sizes for all systems, except here for multi-threaded DuckDB, and this suggests that with larger files, we have more opportunities for instruction level parallelism. Next, let's compare the misses per 1,000 instructions, or MPKI, when loading CSV and GeoParquet files using different systems. First, let's look at CSV loading on the left-hand side. Here we see that DuckDB, both multi-threaded and single-threaded, experiences significantly fewer misses compared to GeoPandas and OGR. Additionally, we see that in all cases, instruction misses dominate over data misses. Now, moving on to GeoParquet loading on the right-hand side, we observe a different pattern. Here, data misses dominate, except for OGR. One possible reason for this is that GeoParquet is a compressed file format, which requires consulting a dictionary for the compression, leading to more data misses. All right, this brings me to the end of the talk, and let me take a minute to conclude. In this paper, we analyze spatial data loading examining how both the system and file format impact loading performance. We also collected some lower-level metrics to understand what's happening inside the processor during loading. Our main findings are that tensor file formats like GeoParquet correlate with higher loading throughput. The overall winner in our experiments was loading GeoParquet with DuckDB. And finally, we found that in the L1 cache, there are more instruction than data misses for all formats except for GeoParquet. Looking ahead, some future work directions include evaluating the impact of different tuning options and loading optimizations. Specifically, in our experiments, we did not tune the loaders for optimal performance, but used the default configurations to compare the performance from the perspective of a non-expert user. However, in the future, it will be interesting to evaluate the impact of different tuning options on loading performance. Additionally, in our current study, we only evaluated the performance of loading entire files end-to-end without running any analysis after that. So, however, if we also consider a query workload, the fact that some file formats support loading optimizations, such as data skipping, becomes relevant. So we would like to explore this in the future. Thank you very much for your attention. If you have any questions or comments, or simply want to chat, please do not hesitate to reach out, and you can see my contact information on the slide. Thanks.